So good morning students. Today we are going to see about a short brief about our unit 2, which is high frequency transmission line, and we are going to see about that necessary equations of transmission line at radio frequencies followed by line of zero dissipation. Okay, so unit 2, high frequency transmission line. So in that high frequency transmission line, we are going to keep some assumptions. So either we are going to send our signal in either an open wire or coaxial wire at frequency range starts from kilohertz to gigahertz. Okay, so in which we are going to make some assumptions like at very high frequency the skin effect is very low, considered to be very low, and the internal inductance will be almost zero. Okay, this is the first assumption we have made when we are able to send a signal in a high frequency transmission line. So at high frequency the skin effect is considered to be very low. Okay, then due to that skin effect the resistance will be increases with decrease of frequency, but the reactance omega L, this will be increases with frequency. Hence omega L greater than or equal to resistance. Okay, this is the second condition. The third condition will be considered as the G may be considered 0. G is admittance here. Okay, so R, L, C, G, these are the four primary constants in transmission line. So for considering the assumption for high frequency transmission line, at high frequency the skin effects will be very less, so that internal inductance will be very low, and due to the skin effect the resistance increases with decrease in frequency, but due to reactance there will be an increase in frequency. So that's why the omega L greater than or equal to R, and the conductance G is said to be low. So these are the three primary consideration will be followed in high frequency transmission lines. So now the line constants for zero dissipation line. As we all know that the Z and Y value, Z equal to R plus J omega L and Y is equal to G plus J omega C. These are the two general line constants for a transmission line. And we know that characteristic impedance Z0. So Z0, which is equivalent to square root of Z by Y, and the propagation constant gamma, which is equivalent to product of Z square root of Z and Y. Okay, so in case of characteristic impedance, square root of Z bar Y. In case of propagation constant, the square root of Z to Y. So we know that the propagation, which is equivalent to alpha plus J beta. So alpha is attenuation factor and beta is a propagation factor. So J is an imaginary term. So high frequency, the assumptions what we made is omega L greater than or equal to R, and where G is equal to 0. So by applying these two conditions, our gamma can be changed as follows. So when you apply these two conditions in our R and Y, you could see that here the R is negligible and G becomes 0. Okay, so the primary line constants Z and Y changes to be only with imaginary factors. See here R plus J omega L, G plus J omega C. By applying the conditions of high frequency assumptions, you will get Z equal to J omega L and Y equal to J omega C. So you get the characteristic impedance as root of ZY. So J omega L, J omega C, you will get cancelled. So the value will be J by, that means L by C. So in high frequency transmission line, the characteristic impedance is purely depends upon the L bar C ratio, which we seen in the previous topic, loading of cable. So L bar C has to be maintained in order to produce a distortionless transmission line condition. Okay, so next, where the Z0 is equivalent to R0 can be given as root of L bar C. So which is the inductance and capacitance at the open wire, the value will be given as these two things. Okay, so here the propagation constant. So gamma equal to root of Zy. So we all know that J omega L, J omega C. So you get j omega root of LC. So by applying that alpha plus j beta equal to j omega root of c, there is no real value. So we all know that for attenuation equal to 0 and beta, you'll get root of LC into omega. So by which we get the propagation constant value as this, which is equal to 1 by root of LC, and so the velocity for a open wire is 3 into 10 to the power 8, where in case of coaxial cables, that velocity is deferred as 3 into 10 to the power 8 divided by root of epsilon r. Okay. So this is what that line constants for a zero dissipation line. Thank you.